exam 2 review. What do you want to talk about? I'll do my intro spiel. Think about what kind of problems you want to look at. I have other ideas if you guys don't have ideas. So there you go. This is the section of the equation sheet. I might have updated some things. So I can compare, but here's what the relevant stuff to us. I think I fixed the little hyphen thing, or whatever, apostrophe thing. How about using numbers instead? I think that should be on the equation sheet that way. And I think I changed this W to a U. Other little things I might have tweaked on it, but this is basically the stuff that we're looking at. F equals ma, linear momentum. We didn't really do angular momentum, but I kept it there for completeness. Work and energy, power and efficiency, and then here's the impulse and momentum with the oblique impact, which is coefficient of restitution. Ask yourself, what kinds of problems? Newton's second law, so the class 6, homework 6, where you F equals ma in rectangular coordinates, and F equals ma in path and polar coordinates. These are definitely ones I think that we should cover, do some review on. Particle work and energy. So we have work added in the friction loss with the different types of potential energy and kinetic energy. Up to the conservation of energy, power, and efficiency. And then we had impulse and momentum. We had force times time and mass times velocity. So there's impulse and momentum. And then we had collisions. So there's the 6 classes that we're basing homework exam 2 on. And here's some of the ones that I think are in the packet or problems. I think I suggest that we leave these for your own work or own efforts. But these are the types of problems, right? So then we have any questions, or you can pick these ones if you want. I think I also put ones from the Missouri University of Science and Technology ones. Hey, here's some that are like similar or in the same vein, or things that you should be able to solve in preparation for this exam. I grabbed them and put them in here. I didn't remember doing it, but interesting ones. So if we wanted to get inspiration for things that could be asked or should be able to know how to do. Some of them seem easy. Some of them might seem, some might be a little more difficult and more time consuming. So, taking requests. Freebird. That's always fun, by the way. We used to scream out Freebird. Hey, we're taking requests. Do a little Freebird. It's a song by Leonard Skinner. This one for the mom. Go ahead.
This was one of the homework questions, and it appeared on the packet you handed out. When you have a mass that is bouncing between 2 springs, why can't you treat it like these springs aren't there? Because the springs are just changing the direction of the energy. They're not.
Because you don't know how far the thing is going to go into. If there's friction, you have to. If there wasn't friction, you wouldn't have to.
But wouldn't any energy that went into the spring be immediately the second it stopped moving?
That's true, but you need to know the distance it travels until the spring stops it.
For kinetic friction on the ground.
But then there's friction on the ground that steals energy away.
Yeah, but that friction would be there if it was moving anyway.
Yeah, but you don't know how far it's going to move.
That's what the question is asking, right?
Without the spring. Because what's going to happen, if you take it in stages, is the fin is right here, the spring's right there, right?
Yeah.
So this thing is moving, right? So it's just about to hit the spring, right? So then it hits the spring, and it's still moving, right?
Yeah.
It has slowed down a little bit between here and here because of friction. Then it compresses it all the way, right? So we have this distance right here, it has moved.
Yeah.
During this time, it has lost energy. We don't know what this distance is until it completely stops. Does that make sense?
Yes.
All right. And then, as you say, it comes back in this way. Now it's moving this way. It's off of the spring. Like this right here and this right here have occurred. This is a smaller velocity than that.
Yes.
Okay.
And the change in velocity would be between there and there would be 2 times the normal force times the coefficient of friction times the distance traveled by, or the compressed distance of the spring.
Yeah. So like you could go like right here we have KE. Let's call this 1. Let's call this 2. Let's call this 3. And let's call this 4.
Yeah.
Okay. So we have KE1. And then it's so right here it's going to be KE2 is going to be equal to KE1 minus friction force. And call this right here, call this delta X1. Delta X1.
Yeah.
Now right here, the kinetic energy is going to be equal to 0.
Yeah.
Oh, not equal to 0. So kinetic energy 3 is equal to 0. Because it stopped. Because its velocity is equal to 0. But we have potential energy at 3. And that is going to be equal to, and let me also say this is going to be, I'm trying to think here. This is going to be, I'm trying to think between here and here. I guess I'll call this delta X3 is going to be equal to 1/2 K delta X3 squared. But that's also going to be equal to kinetic energy 2 minus friction force times delta X3.
Yeah.
So you have this amount of kinetic energy right here, right in this state, but then it traveled delta X3 until it got to where it stopped. Then when you're going to have kinetic energy 4 is going to be equal to potential energy 3 minus friction force right here, X3. So there's going to be 2 of these, right? This is not the same one as this, even though it will be the same value. It will have moved out this amount right there.
Yeah, but I still don't. Can we apply some numbers to this to solve it out? Because I still feel like.
Okay. I mean, let's make this. I got to make it large enough so that it will return. The K is always with the thing that that's where you have a possibility you pick the wrong K. You end up making that. Yeah. All right. So the problem with trying to find, you see, we're going to have to try to find what KE3 is going to be.
Yeah.
I mean, not KE3, delta X3. Delta X3 is so that we have to do a quadratic to be able to find it.
Yeah.
All right. So if we were to say this V1 was equal to, I don't know, let's make it really big, 100 meters per second, and make this guy here, make his mass 10 kilograms, and let's take this square-in constant and make it pretty small, so that this might make a lot of squishiness. You could say, you make them 4 newtons per meter. That's like barely nothing. So the kinetic energy is 1/2 mv1 squared. So 1/2 10 times 100 squared. 100 squared being a lot. 10 times 2. Probably not choosing very good numbers, but that should be 50,000 Newton meters. Then when we get to right here, probably, I don't like quite the way that I was writing it. I was riffing and decided to write the thing onto there. But it's better to write like, no, I guess that's fair. In between here, we're moving from there to there. This is kind of an unnecessary one, but we'll say that this thing has that delta x1 was 1/2 meter. And because of this, let's see, f of f is going to be mu, which we'll say that mu is all of 0.3. Mu k, that would be. And this thing, so that's going to be times mg, because it's Fn. So 0.3 times 10 times 9.81. Hopefully I didn't mess up with the numbers. 9.81. We go times 3. Oh, it's not a lot. 29.43 newtons. Yeah, I'm correct. Okay. And so in here we're going to have KE1. KE2 is going to be 50,000 minus 29.43 and then times 0.5. So 0.5. So it's not big, it doesn't make a big difference. 49,985 Newton meters. Now this is going to be the difficult one because this is all going to turn into potential energy. So what you're going to have is you're going to have KE2 minus FF delta X3 equal to 1/2 K delta X3 squared. And we're not going to know what delta X3 is because this needs to be enough to have slowed everything down and turn all of this kinetic energy into potential energy, but some of it's going to be robbed from the friction. So you have to go back up over here and go, so 49,985 minus 29.43, double this change in position between 2 and 3, we'll call it delta X3. And then over to here, where it's going to be, the kinetic energy is 0 when the thing pauses for a second. And then it's going to be 1/2, and then we chose a really small number for the K, and that's a delta X3 squared. So basically, we're going to have the quadratic of 2 times delta X cubed squared plus, because it's going to go on the other side, 29.43 delta X cubed, and then minus 49,985 equals 0. So for the delta X3, we're going to get negative 29.43, I'm using the quadratic equation, plus or minus the square root of 29.43 squared, minus 4 times 2 times minus 49,985, whole thing divided by 2 times 2. I used to hate this so much, but I got used to it. 4 times that, so it's 8 times that, and then 29.43 squared, and we're going to add them together and square root them. Alright, so I like to write this number down, usually someplace. I don't always show it, but 633.05. And so we don't want to go minus and minus because that doesn't make any sense. So we'll go plus and that, so we're going to subtract out the 29.43, boom, and divide it by 4. So what we say, this is a ridiculous value of about 150.9 meters.
Yeah.
That's just because I picked a really, really stupid spring constant. The spring constant is probably the one that's driving me.
Yeah.
But it was a large 100 meters per second. That's very, very fast, isn't it?
Yeah.
I just didn't want to make it.
Yeah.
You risk making. Yeah. So anyway, so that we get this, and then for the next one, as we want to find the kinetic energy of the next state, it's going to go the same distance again, and the potential energy is not going to change. Potential energy doesn't change right here, but it does change. It's proportionate to the potential energy change. So you're going to have KE3. Let's see. I'm going to write this other way. It's going to have PE3 minus, and let me write it right. So it's going to be same deflection. It's going to be 1/2 K delta X3 squared, and then F times delta X3 is going to be equal to 1/2 MV4 squared. And the difference here is that this doesn't add back. This subtracts again from the other guy.
Yeah.
So it further reduces the energy. So 1/2 times whatever the hell it is, 4 times 150.9 squared minus our 29.43. This isn't going to, well, it might, it's going to make a big difference. Get that 150 thing. 1/2 and then 10 and then V4 squared. So you have V4 is going to be equal to, let's see, you're going to do that twice. So square it times 2, boom. Flip it and multiply it by 29.43. Boom. Subtract it out and divide it by 5. Divide by 5. And then square root it. And so we have 90.67 meters per second. Does that make sense? Did that solve the thing that you're...
Yeah, can we now just get the total distance that it traveled?
The total distance that it traveled would just be from where?
From where it started, the total distance it traveled.
Okay.
And that's what I'm confused about, is that why it wouldn't be the same if the string wasn't there.
The total distance that it traveled, why wouldn't it be the same? I mean, after the fact? You mean after the distance it would travel after it's left the spring?
I think it travels the same distance.
The total distance it travels, the distance equal, like the total distance that it was compressed going in and out, why it would be the same if the spring wasn't there and it just kept going and there was no wall, it just kept traveling, why that distance wouldn't be the same as...
Oh, I see what you're saying. Okay.
Because on the homework I did it just via, it was asking for total distance traveled by the block.
Okay.
As
So you're just saying that like as the spring comes in and out.
yeah.
Isn't the same with block travel the same distance?
Yeah.
I think it would be the same distance.
I got a different distance from you on that, but that might be a math error on my part, so.
Could be that error on my part. I see what you're saying though, right?
That's what I was confused about.
Okay. Let me think. Because you recoup all of that. Yeah. But you wouldn't know. You wouldn't know where it would end up, though. But that's either here or there. I didn't really ask that. I could have asked what position it ended up with, and then it would matter.
Yeah. But just total distance traveled.
Mm-hmm. But I wanted you to do this. I wanted you to do this. That was the whole point of the thing. You're trying to bypass the point of the problem.
Yeah.
Yeah. It's a technicality, I guess, yeah. I guess it would be the same distance in the trail.
Okay.
But I have a problem that's like, what is the change in distance from the start to the end?
Yeah, I mean, where did it end up from this thing, and then you'd have to do this.
Yeah.
Then you have to have a spring.
Yeah.
It's kind of far away, there's not much displaced time, speed to this is not.
Okay.
Yeah, that makes sense.
All right. Any other questions?
Can we do a friction, just a friction loss problem with work energy? Just a mountain with an initial speed, and how long we travel with work energy?
Sure. You want to put out a slope or anything? Or?
Yeah.
I mean, it's up to you. Is there a force on the thing, or just?
Yeah, I think she learns. Well, I just want to be more comfortable with work energy.
Okay. All right. Trying to find one where we could actually get the answer. Because I was like to have. See, now this one right here, this probably, you know, how high this thing goes back up. That's a tough one right there. That's the one that's kind of like similar to what we were just talking about. I decided not to give you two angled ones. That's the reason why I gave you between two springs. That one's too, maybe a little bit too much like the one we just did. It does require a quadratic in there, and it has a trick in it too, I think. So we're probably not going to find something like, well, maybe, let me see. Look at, this doesn't have numbers in it. Yeah, so my problem, thinking problem is a little bit like a source. I'll just make something up. Unless I had one here. I had, can't remember who's, I think it's going to be Dr. Rico's exam. Yeah, that was Dr. Rico's exam. We can do other problems. All right. So, let's say that we have a block that's moving up this slope, and it's moving with a velocity of what, US units or?
Yes, because we'll do it.
You want to see it? How much does he weigh?
5 pounds.
Say what?
5 pounds.
Tons or pounds?
Pounds.
Pounds. I can't hear you. I'm sorry. My hearing is going. How fast do you think he's moving?
15 feet per second.
That's a lot more reasonable than 100 meters per second.
Yeah.
And what do you think the slope is?
76 degrees.
76 degrees?
Okay.
Okay. I wish I'd drawn it like more like 76 for sure. Okay. So we want to find out how high it's going to go. Is that reasonable before it stops? Pauses and it comes back. It would be interesting, how high does it go and then where does it stop on the way back down? Right? Or does it? Maybe, well, we don't have static friction, so what's our coefficient of friction? We pick that. 0.2. Okay. It's going to go pretty high, I think. All right. So, we could even draw it up here and then say, how high does it go? Good idea to draw an FBD somewhere. Get your angle the right way. Your angle is going to be looking like something like that right there. So we have a weight. Remember, the ground isn't there, so I was just using that for reference. We're going to have a normal force and a friction force right there. And so right here's our angle. So right here's our angle. So the sum of the forces, and obviously it will be a little bit pedantic. Draw a correct three-body diagram. Here's our x prime and a y prime. So some of the forces in the y prime direction equals mass times acceleration in the y prime direction, which we know is 0. So we'll come up that way. And so we'll say that the negative weight times the cosine of beta minus or plus Fn is equal to 0. So Fn is going to be equal to the weight, which we said was 5 pounds, times the cosine of 76. It's a 76 cosine. I think that's right. 5 times. We only have 1.210, call it pounds. So the friction force could be mu times Fn, or 0.2 times 1.210 is going to be small. 2 times. So 0.2419 pounds. And then we will say that we have KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. Start putting them together. So we're going to have 1/2, well, I guess I usually do it on the list of stuff. KE1. 1/2 MV1 squared. 1/2 5 divided by 32.2. 15 squared. So 15 squared times 2.2. We have 17.47, and these are foot-pounds worth of energy. PE1 is 0. U1 to 2 is going to be equal to negative friction times delta x prime. Right? That's that distance. What's that?
Nothing, sorry, just thinking about it. Sorry. I was thinking of something.
Okay, cool. Well, it might be easier if we're gonna solve for H. If H is what we want to know, we can probably, you can pick and say that, let me think about that. H is going to be equal to delta x prime times the sine of 76, right? Because this would be, that would be the hypotenuse of how far it's going to move. But we want to solve for H, so we might as well just put it in terms of H. So we can divide H by the sine of 76. Negative FF times H divided by sine of 76, which we could make as a number. I don't know why I did that. But anyway, you go 0.2419 divided by sine of 76 times H, and 76 sine divided. Boy, that doesn't change that much. I guess 76 sine. Yeah, that's close to that. Okay. So negative, I put the negative inside the sum. 0.2493 H. And then kinetic energy at 2 is equal to 0. So you can pause. And then so the potential energy is then going to be equal to weight times H. All right, we usually go mgy, but that's what basically the thing comes out to. So just 5 times H. So you plug them all into this equation down up above, and you get 17.47 plus 0, just to give a spaceholder, plus negative 0.2493 H is going to be equal to 0 plus 5 H. So that's that 5 is going to add into here, so you're going to bring that over here, and 5 plus, and nope, that didn't work. Did I do something wrong?
Why is it?
I think that should be 2 point. That's what happened. I'm looking at my calculators. Just because the mode I have it in, it doesn't always do me a lot of favors. 2 point, what did I have? 493, yeah. 493. I think that's correct. Yeah, because I divided this by, no. Let me just double check my numbers, I'm sorry. 0.2419, 76. Yeah, that should have been right. What the hell happened? Okay. Say again, please. What?
Well, I couldn't figure out why you had your work as negative, because I just put it on the other side of the equation, so it'd be positive. I couldn't figure out why you had that negative.
Because you can go back to that.
Yeah.
Okay. I think I just hit the wrong button like 3 times. 3.3 to 8 feet was that, and I thought it would be a lot higher.
The angle.
The P angle, yeah, the angle's pretty high. So that would be what the results. It's kind of a trade-off. Really, the friction didn't really matter all that much because of the. You can see that this right here actually goes on the other side and adds to it, and then you divide. What way you divide out further to make that for a smaller number. One problem or set of problems we haven't done a lot is the different configurations that you could possibly have in Newton's second law. So I just want to point out some of them.
I just have a question on like the most and homework one you said.
Okay.
So in the first question, we are given an angle of 30 degrees, but the velocities are going in the neutral in the n-axis.
Mm-hmm.
When do we? I know we have to use that 30 degrees probably to find the tangential of them bouncing off each other, and then with that you can find like the total velocity and the angle at which they're going. Where do we put in that 30-degree angle?
All right. Well, we want to. All right. So that 30-degree angle is like something like that right there, right?
Yeah.
But this thing's moving in that direction, and that thing's moving in that direction. So what you need to do is we would rather know what these two, and I'll just redraw them out there. That this thing could break that down into components that way and that way, and you could break this down into components that way and that way.
Oh, so you're changing which way the N and T axis are?
Yeah.
Based off
Yeah, this is N, and you could call maybe that T.
Oh, okay.
So you got T and N. We might even call them E, N, and E, T. And so like here's the original vector, but he has a component in that direction and a component in this direction.
So you always put the n-axis through both of them touching, and the T is just the perpendicular to where they're gliding. Okay.
Yeah, so you draw you would like right through the centers of them, and that becomes the normal point. Because remember, the purpose of it is that we're just gotta look at it. We're treating it like just a collision that's directly head on in the normal direction. And then the tangent direction is just along for the ride. Alright, so this, right around here is where they start doing, path and polar coordinates, right? So up above, everything's in rectangular coordinates, and then everybody starts to come down here. So like I had asked this problem before, and students got really flustered with it because they hadn't done one like it yet. And I didn't think I assigned one like it yet. So for full fairness, I sometimes want to ask a problem like this. Similarly, we could do that problem. Similarly, I have asked a problem like this before. And you're like, well, why is this a normal and tangential problem? Did I ask a problem like this? Right here where we have like a car going around a curve, it's got a 1,000-foot radius, and it's rated at a speed of 120 miles per hour. Knowing that the race car is skidding on the curve when traveling at a speed of 180, determine the banking angle and the coefficient of static friction between the tires and is not sliding. It starts skidding. He starts skidding between the tires and the track under the prevailing conditions. The minimum speed at which the same car could negotiate the curve. Do you know how to do that? could you figure out how to do that? You want to know how to do that.
Yeah.
All right. Well, for one thing, this Kyle had upset me about the book. He said that no one's ever made him use the book. He's never had to use the book in any other class. I don't want to be that kind of person. There is a case study example where they have a car doing this thing. And this guy right here just steals everything away right here. This right here. The idea in any of the car problems, car skidding problems, is, let me go back to the problem here. It's a right. This is 1252. We have a car. I don't know. Doesn't matter. Doesn't matter what it looks like. Okay. And we have an angle. And we're told, given that the radius, I guess we'll call it R for the time being, 1,000 feet, and the rated speed. Okay, so the curve has a rated speed is going to be 120 miles per hour. So the definition of rate speed. So we have to look that up here a second. You go at this, the car starts skidding on the curve traveling at 180 miles per hour. And we want to find data. I'm trying to remember off the top of my head right now. So that's A. I should have written it a different way. B is find that, and then find V min. And this is the static coefficient. Right, so look at the static. And just a reminder, we want to take a look at the definition of the rated speed. Well, did it say this is an example, or did it say we go to case study? Oh, no, it's an example. All right, here's the example. The rated speed. All right. Determine the rated speed of a banked highway is the speed at which a curve should travel to have no lateral friction force. No lateral friction force exerted on its wheels. Okay. So, first off, when it's going around a curve, like right there, right? Here's the car looking down at it. And if you were to take an FBD of this and an IBD of the car right here, you would say, first off, let's not worry about this. This is the tangential direction. Here's the normal direction. So it's going to have an M traveling this way right here, M times the acceleration in the normal direction. It's likely going to have, I'll put a dashed line in there, a force in this direction, a force in this direction right there. Some type of friction force that's taking place. But this thing is on a bank. So we can't really, this isn't really a useful FBD and IBD for us. We don't get the full picture in that position. So instead, we're going to draw the FBD and the IBD in the plane looking in that direction. Here's the creepy eye looking in that direction. So we have a car, which I'm going to draw poorly, and a car And when it comes to this, it's going to go in that direction right there. The mass times the acceleration in the normal direction. Going towards the center of the curvature. That's the reason why I drew this up here. Because it's kind of weird to do it from this point of view. But we could draw our N, and that could be our Y right there. Our normal is going towards the center. And so here we have a weight coming in this direction right here. And then we could have, I'll just draw a Fn taking place right there. So yeah. We're not going to draw a friction force in this plane on this FBV because of the definition that they said the rated force, the rating system is that's how fast you have to draw in there. So you don't need any kind of friction force. You don't need a friction force that would keep the car from sliding down. And you don't need a friction force that would keep the car from sliding up. So think about the two scenarios that are possible here. Think about a car that's standing still, right? A car that's on this bank. It needs, if you just had this right here. If you just had a 3x-diagonal, it's a statics problem. Car is not moving. There needs to be a friction force going upwards this way to counteract the component of the weight that's coming down this way, right? If this was greasy, this car starts sliding down. Or, if this was really, really greasy, and this car is running around the track, it's going to go wee and slide up right there. But they say this rated speed is one in which you don't need a friction force. All you need is this thing to balance out. So I guess maybe the way that I would look at this, let's see, here is the angle right there of the bank angle that you need. And so if you close it, that's going to be the same angle as this, which is the same angle as this. Yeah. So they told us that that rated speed of 120 miles per hour, we could turn that into, and we need to turn that into feet per second. So 120, what's that? 5,280. I get that right? That's feet per mile, and then divide by 3,600. And so you get that to 176 feet per second. So we'd say the sum of the forces in the normal direction is going to be equal to mass times acceleration in the normal direction. Well, in the positive direction, that's going to be well, let me do it first. Sorry. I need the. There's probably a trick, quicker way. But in the y direction, mass times acceleration in the y direction is going to equal to 0. And so what you can say is Fn times the cosine of theta. I feel like my angles are wrong. No, I think I'm okay. I don't like it. It's the cosine. I feel like they shouldn't be the same. That doesn't feel good. Something's wrong here. Fn should not be equal to that. Okay, yeah, okay, then, okay, I got you, I'm sorry, my brain's not working. Yeah. Yeah, I got it, okay. Fn is equal to, the weight, which they didn't give to us, that's fine. It's okay they didn't give us the weight. Divided by the cosine. Yeah. In the y direction. And then, sorry. Some of the forces in the normal direction equals mass times acceleration in the normal direction. And you're going to have a component in the left, because you're going to have Fn times the sine of theta is going to be equal to m times v squared over r. I should have probably put this as go mg for the weight, cosine of theta. So you can replace this Fn right in here and say mg times the sine of theta over the cosine of theta equals mv squared over r. And what you end up with, you get the mass cancels out, which is always kind of surprising, but kind of makes sense. The track can be rated for any kind of car, so it doesn't matter in the calculations you find out when it comes to the rated speed. And so this turns into the tangent of theta is equal to 176 squared divided by 1,000. 176 squared divided by 1,000. And so it ends up being, oh, I'm not liking this, so that's okay, 30.98. So you take the inverse tangent of that.
You can specify by gravity.
Oh, yeah, gravity, divide by gravity, sorry. G, yeah, 32.2, thank you. I needed that. Gravity, 32.2. Good, okay. 176 squared, 1,000, 32.2. Alright, so that's going to be 0.962. You take the inverse tangent. Alright, so there's an angle that makes sense, or maybe a little bit. 43.89 degrees. That's the angle so that you don't need any amount of lateral force. But now so that's like the answer to the first part right here. And I think, they said at 180 miles per hour it starts to slip, right? So it starts to slip means that's right. So that means that the thing this starts to move up, right? So we redraw the FBD. And we have the car. Still have the MAN as part of it. And now we should still have the same normal. Well, we never found the normal force actually. We had the same equations for the normal force here. But now, since it's going to be moving this way down there, the friction must be coming that way. Did I get that right? And as it starts to slip, FF is going to be equal to the coefficient of friction times Fn. And you notice once again, they didn't tell us what the weight of the car is going to be. Still did that. So we still can do the same. I guess I'll go ahead and stick with this. Yeah, we'll still do this direction. It makes it easier. So yeah, so we have to be a little careful here. We have because it's almost better. Sorry, I'm hemming and hawing, and the best way mathematically to do this quickly. I think it'd almost be better served to rate it. Yeah, I'll just keep it with this orientation. That's fine. So here's the angle, and here's the angle. So there's theta right in there, and there's theta right in there. So you could go, do I need to put the weight? Yeah.
We're considering friction to be static when the car is moving. Because it's moving in that direction.
No, okay, so the static friction is really sort of like this trigger, right? You multiply the coefficient of friction times the normal force, and now you go, if you get to this level of friction force, it will start moving, right? So if they use the words to say it starts slipping, you can multiply by the coefficient of friction. In this case, we're trying to work backwards to try to get it. And I'm sorry if I'm hemming and hawing here. I'm trying to think about like what's going to be the easiest so it doesn't give me some tedious cosines and sines to go through this. I would prefer personally to no matter what, it's going to be easier to stay with it. I didn't even write tangent in the y direction. So I'll do it in the y direction first. So the sum of the forces in the y direction is equal to mass times acceleration in the y direction, which is 0. Right? So that's got to be the way. Right? So sometimes it's easier to tilt, but if you tilt it, you're going to have a component of the normal acceleration in that, and you don't want that. You know, it's not going to kill you, but this will be better off. All right. So what we'll say in the y direction is we're going to have negative w, but we're going to have plus Fn times the cosine of the angle we just said, but minus mu, I'm going to replace the ff, mu times Fn times the sine of theta equals 0. Are you okay with that? So yeah. And make sure we have this as mg. I don't like that. Okay, so what we could do is now we can go Fn is equal to mg divided by cosine of theta minus mu s times sine of theta. Is that okay? Now we come back up to the top and say sum of the forces in the normal direction, mass times acceleration in the normal direction, and in the normal direction, so be horizontal. Well, W doesn't show up anymore, but we have a Fn times the sine of theta. Right, that's going that way, and then we have plus Ff, but instead of Ff, I'm going to draw mu S times going to the right, right, equal to M times V squared over R. So let me rewrite this quickly. Sine theta plus mu s cosine theta equal to mv squared over r. And then we can replace this back into here and go mg sine theta plus mu cosine theta divided by cosine theta minus mu s sine theta. It's going to be equal to m v squared over r. You'll notice that the m's cancel out again. And we'll be able to solve for mu. Not a lot of fun, but we can solve for it.
Why would the normal force be at all dependent on the frictional force?
Why would the normal force at all be? Oh, that's a good question. Why would it be dependent? Oh, well, for one reason, because it's dependent on the speed.
Okay.
It's somewhat dependent on the speed, and the friction is dependent on the speed. So they're kind of linked by that.
Okay.
Because up to, I think that's how I would say it. That I have to write this one in the vertical direction to avoid that.
Yeah.
With a normal force,
I don't understand why it wouldn't just, the normal force would just be, what is it? Mg's, cosine theta.
because it has, well, for one thing, you have to separate out, this is the trigger normal force, for one thing.
Yeah.
And no, it's also because of the nature of that the car is, this is going towards the center right here, and this thing is on a plane.
Yeah.
So there's a certain amount of, there's a component of this in that direction.
Yeah. Okay.
So in order the friction is going to be changing. We're really trying to find this.
Yeah.
Yeah. But I hear what you're saying. That's a conceptually difficult one to try to swallow.
When you're doing the efficiency problems, you can't get above 100%, right?
No.
Okay, so if you get anywhere above
Anything 100%, you're just patent it immediately. Become rich and powerful.
Yeah.
Or check your measures.
Watch your back.
Watch your back. People are going to be coming for it. So anyway, this was a little bit more tedious during an exam, as opposed to this right here, which is very deceptive in its simplicity. So I do want to try to just one last thing on here. We would do, just to torment you more, you would do it close to being the same, but you'd probably be better off drawing an entirely new free body diagram and working through it with this part C.
Yeah.
Because you would need to draw this, but now with the friction coming up this way. And that would be the minimum speed that you would need to go so that you wouldn't start sliding down towards the center of the track.
Is that 120 or no? Is that not 120?
No, 120 when there's no force on it.
Okay.
When there's no lateral force, either, keeping you from sliding down or keeping you from sliding off.
Okay.
But it'll change one of the signs inside this second part of the problem, but you don't want to just rely on, you're better off trying to be organized by making another free body diagram.
And there is a first stage, I think the last.
This guy?
Yes, the last one.
This is suspiciously large right here. I wouldn't have thought that it would be that close to 45 degrees.
Okay.
So their numbers might be a little off. So anyway, we have this hammer throw guy, 1237. And they're throwing a hammer, and I guess I'll try to draw the two. Just a little bit. There you go. And he's spinning around, and they say that his radius of his spin, they're calling it, they're actually giving you the thing. Wait, are we supposed to find it? Let me think. Oh, no, we want to find the radius, we want to find the tension. So first off, the mass of the hammer, or it doesn't look like a hammer, looks like it. It's going to be 7.1 kilograms. Oddly specific. And it's going to spin in the horizontal plane. Spinning in the horizontal plane and making a circle. And we know that this is 60 degrees right here. And that the speed is 2.5 meters per second. So we're going to find the tension in the wire and the radius of the circle. So this is want to find it. We have a V of 2.5 meters per second. With an angle of 60 degrees. That was part B. Part A is the tension, Ft. So, we could draw the free body diagram looking down at him, but it doesn't give us enough information. So it's going to be better actually to do a very similar thing to what we just did, and have the look at it from the side. And from the side, so we have a normal going towards the center, and let's go Y. And the tension goes up to there. And we're going to have mass times gravity. And the only acceleration we have is mass times normal acceleration. And right here we have the 60 degrees. So actually part A is pretty easy.
Yes.
So all I need to go is Ft times the sine of theta minus mg is equal to 0. This is not going up or down, it's spinning in a circle constantly. So Ft is just going to be equal to mg over sine theta, or 7.1 times 9.81. Divided by sine of 60. 0.43 newtons. Then take some of the forces in the normal direction, you know, mass times acceleration in the normal direction. And you have Ft times the cosine of 60 degrees is equal to, well, that's just the theta, but I'll put it in there anyway. 7.1. Just lost my place. What was this other thing we're supposed to find? Oh, the tension in the cable and the radius. Okay, cool. So the tension is going to be 80.43. And the speed of it, so it's going to be, I should have written this out, sorry, anyway. 2.5 squared divided by the radius. I should have written in this right here. It would have been better to write cosine of theta is equal to mv squared over rho. Should have written that in there. But you get the idea. So times 60, cosine should be 0.5, right? 7.1 divided 2.5 squared and divided. No. We'll get the inverse back. Yeah. So is it 1.104 meters? 80.43. 60 to the 7 times 7.1 divided 2.5 divided. Yeah.
What did you get?
I got 1.104.
I got 1.104.
Sure. The harder question is to not ask that. Yeah. By doing this, you kind of lead you to this conclusion. I would tend to not ask that. Because I'm not measuring dynamics as much as problem solving. And so this right here is sort of a leading question. You would kind of need to know this one in order to get this one. And so like sometimes, one way I would do it would be to tell someone that here's the braking strength. So okay, so I think I can ask this problem. I'll tell you the braking strength. What is the velocity in the angle? I think I can do that. I'm trying to remember.
So T.
Did I get that? Like, give the braking strength. So like here's it. So what's the maximum velocity? And I gave the
You
angle.
need R.
You need R. Maybe I gave R.
And you need to have two unknowns.
Yeah.
Yes. Yep, M, we have G. If you're at.
I think I gave the angle and the braking strength, maybe. The angle and the braking strength. But you still need R. No, if you have the angle, no, you still need R.
Yeah.
Yeah. I must have given the angle and the braking strength. No, the tension in the braking strength. Yeah.
You have T, M, V squared, or V, R, theta, and you'd have to ask for two of those.
Yeah.
You'd have to get those.
Well, I could ask for only one thing, and you would need to know.
You would need to sometimes give us all but two of them.
Yes, all the two of them. Yeah. And the radial, sometimes it's a difficult one to But most of the time, the idea behind it is you need to know the variables of interest. Or, in any of the N2L problems, the whole idea at the center of it is to, kind of like try to think your way through how the coordinates can separate for each other and be able to get you, the unknown, cover up the unknowns that weren't provided. Like, I think this is a little straight. This one's actually hard because of the free body diagram that you have to draw for the thing, as I recall. Yeah, but what you have right here is you have this parasailing system uses a winch to let the rope out at a constant rate so that the 70-kilogram gutter moves away from the boat, which is traveling at a constant velocity. At the instant show, the rate, the rope has a length of 30 meters. It is increasing in length, right? So that should be a clue. That's an R dot, right? The angle is increasing at a rate. So now you have the angles increasing at a rate of 0.05 radians per second. So that's and by the way, that's clockwise. So in our calculations, that should be negative if we're going to keep things correct right here. And an increasing rate right here. So this technically should be positive because it's getting slower, this angle. Its speed at which it's increasing is slowing down. So for us, clockwise is positive, so that's kind of a confusing thing to put in there. Knowing that when the rope makes a 30-degree angle with respect to the water, the tension of the rope is 10 kilonewtons. Determine the magnitude and direction of the force of the parasail on the parasailer, right? So you have to kind of like look in there and picture what that, a spot, because you see all these cables right there. So imagine it all came down to one spot, and then maybe one rope, and then think about that's the force like right there, and maybe the hitch being put onto there, because it's a tough, it's kind of a tough problem in some respects, is just visualizing how that works. But when everything is said and done, it's all about the free body diagram of the problem, right, and the IBD, and then working through all the, make it like a little dot right here, and say, here is the force of the tension right there. And I'm trying to draw that in there so that you can have a reference angle. But here's the angle that they were talking about right here. And so that's going to be the R direction. And here's going to be the E theta direction acting onto the thing. Of course, you have gravity, mg, acting onto the plane. And so now you're going to have a unknown coordinates right here of FR and F theta, if you call it. And then you're going to equal over to here, and here are going to be the accelerations, and you should really just go M, AR, and M, A theta. But then when you go to find AR, remember that it's going to be R double dot minus R theta dot squared, and then A theta is going to be R theta double dot plus 2 R dot theta dot. And one of them, I think they said this was a constant. It is increasing in length as a constant, this. So that means that's 0. Does that make sense? How you would approach the thing? Yeah. And then you end up right here. So Determine the magnitude and direction of the force of the paracel. So you're going to get these two answers right here. Recognize that one of them is going to be, this right here is going to be negative. So I just drew this in the positive direction. So the actual thing that you would value that you would put in for AR would be the negative value right here. That's, you know, and this is one of those cases where I would use a sign convention to try to keep the thing, to keep track of stuff. All right. So what do you want? What kind of problem do you want to do there? You got half hour left. Is that right?
I gotta get going.
Okay.
I need to do 15 minutes. I can do one more problem.
Okay. What kind of problem? Somebody named Diego something just commented on one line.
He lives in a day.
I don't know if you see that. What kind of problem? Did you just get that?
I can do another one. I don't care which one.
Okay. You can share.
Is the stuff that we learned in class on Thursday going to be LinkedIn?
No. Yesterday, no. That's Angular. I haven't written the homework yet for that. I'm going to try to post it before I leave today. Even though I don't think anybody will work on it.
Can you make it do next Thursday?
Yeah. Yeah.
Did we do one that was like, I think you did because I was coming on at the spring block. The combination that there was a problem 13.2 where it's like a false swing and then a spring at like an angle in the class 11 notes.
My brain's not working and I'm not quite sure.
You think they put you on like
Oh, okay, yeah. We haven't actually done that one, have we?
No. Or is that like a lot for it?
That is a lot. That is a lot, but it's a good problem. What is it, 13,200?
Yeah. There's a video with 4 minutes long.
Is it really?
Yeah.
Wow. Yeah.
Then we don't do that one. I just saw it and I knew that we had to.
Gotcha. It's a, one we haven't done is a pendulum problem. That's a good one. The ballistic pendulum. A ballistic pendulum is used to measure the speed of a high-speed projectile. A 6-gram bullet is fired into a 1 kilogram block suspended by a cord by a length of L equals 2.2 meters. The block block then swings through the maximum angle of 60 degrees. Determine the initial speed of the bullet, the impulse imparted on the bullet, on the block. Does it tell us the time? When I get to this is the impulse. They're not the impulse force, they just mean total impulse. And the force on the cord immediately after the impact. The force on the cord immediately after the impact. Okay, that's an interesting one. So this is a good problem because it's not impossibly difficult, but it makes you think through the thing. And it's a real one. It's a real thing. It's a ballistic pendulum. So if you're looking at 13.152, and we have this pendulum hanging down there, there's a bullet traveling through it, and at some time later, by the way, the bullet embeds. What you have to do is, and we find out that the length here is 2.2 meters. That's a lot. And the block B is 1 kilogram. And the mass of the bullet, I like that little b, is equal to 6 grams. And the angle theta is equal to 60 degrees. Determine the initial speed of the bullet. So you're going to find VO. And that was actually the purpose of a ballistic pendulum, is to try to estimate what a muzzle velocity is. Of course, obviously it's slowing down as it goes through the air. So that's going to be A, and B was the impulse, and then C was the FT after collision. So the thing to do is to work backwards with work and energy. You see why? Because this kinetic energy right here turns into potential energy. So we go, and actually I'm going to call this KE2 plus PE2 plus U 1 to 2 is equal to KE3 plus PE3. So we'll establish this is going to be state 3. State 2 is after the bullet has hit it. So you go, I'll just write the thing out to make it quicker. PE2 is 0. We'll say there's no difference between 2 and 3. KE3 is going to be 0. So basically what you have is you're going to have mg, and then this delta y right here, this delta y, and that delta y is going to be, delta y, and that's going to be equal to L minus L times cosine of theta. That happens a lot. So you'll notice that that's, and this mass right here should be the mass of the bullet and the block together. So 1/2, I did that math in my head, 1.006, right? V2 squared is equal to 1.006. Notice that cancels out. That's interesting, right? Times 9.81 times the length, which is 2.2, times 1 minus the cosine of 60. So I don't like that cancels out. How did you? That bothers me.
It cancels out here, but it doesn't cancel out in the momentum that you're going to do later.
Yeah, move on a step. Yeah.
The mass is constant.
So 60 cosine 1. Oh, that's easy enough, right? That's 0.5. Yeah. Okay. 2.2 times 9.81 times 2 times square root. So that's going to be V2 is 4.646 meters per second. And that actually, no, it doesn't answer. That was an answer. Actually, we can actually use that for part C, because that's going to be centrifugal acceleration, interestingly enough. Okay, but anyway, now we're going to go impulse and momentum, and have bullet versus block. So before impulse, after. So you go the impulse, kaboom, they go away, and after they go together. So you're going to go MB VB1. This guy is stationary. These guys cancel each other out, and they're going to go MB plus M big B times V, this would be V2, the thing we just found right here. So you're going to get the 9 grams VB1, which is what we want to find, and we have 1.006 times 4.646. So 1.006 times 0.006 divided. And so we have on VB1 is going to be 778.9 meters per second. Does that make sense?
Yeah, I just got a very basic, but.
Oh, I'm sorry. Maybe I screwed something up. Did you get the same velocity?
Yes.
Let me try again.
Oh, I put the wrong math, but.
Okay. And, so what we would do now instead for the impulse. Ooh, how do you get the impulse? The amount of impulse. What you need to do is you need to leave off one of the parts. That's tough because this thing is there. But what we would do is you essentially would ignore the bullet and just look at the box by itself. And what you would say is you would go box plus some impulse acting onto the thing is going to be equal to box moving at that amount. And that impulse would be force times unit for the thing. So you're basically saying imp equals one. That's kind of a stupid thing. I wonder, I wanted to answer the back of the book. Times your 4.646.
Wouldn't it just be 1 kilogram?
Yeah, I think you're right, yeah. You leave the bullet out of it. So it would just be equal to this. That doesn't make any sense. Is this one in the back of the book? But let me just finish off the idea there with the last part of the thing. All they're wanting is they want the tension. So we have the block with the bullet in it, and we have the tension coming up. So your FBD and our IBD. And we have weight onto the thing. And here we're going to have, well, we don't really care what's going in this direction. We'll get the mass of the normal acceleration. So some of the forces in the normal direction, which we assume we can make as positive, make that tangent, because it is moving in that direction. We could say that there's FT. Ft minus W is going to be equal to mv squared over, we could call it length, right there. So it's just going to be mg plus mv squared over L. Or if you wanted to be very, very specific, you could probably leave that off as an estimate. But we have the velocity of 4.646 squared, and the length is 2.2. So you can find what the answer is. All right, have a good weekend.
Will you be posting like the 11 answers?
Yeah, it's due today, right? Yeah. So I have it set to go off at midnight.
Okay, good.
Yeah.
And then does the video capture the papers, or do you post the papers too? When you post this online?
I'm going to put it on YouTube.
Okay. Thank you.
You're welcome.
Have a great day.
You too. I wonder if this thing worked. anybody show up? Oh yeah, there's somebody there. Thomas. Hey Thomas. Hopefully the microphone worked.